Today we're going to be looking at some results that are obtained when you use different spark gap configurations for the resonant circuit part of this design. Basically what this video is stemming from is the first spark gap that I was using in my videos, where it was the three copper pipe sections making two sort of gaps. I was pushing that spark gap pretty hard, and I believe what happened was there was some sort of carbonized path that formed in between the mounting bolts for the copper tube sections, and the wood that the mounting screws were screwed into became conductive. So that spark gap no longer worked, which forced me to use some other spark gap designs just with some materials that I had laying around, and I did create one that I'll go over here pretty soon, and notice some not optimal performance issues with it. And I've created another one, which is a multi-gapped spark again, that has better quenching properties, and we're going to go over some of the pros and cons of some of the different spark gaps that I've been using so far, and sort of identify which one is the best one for this experimental setup. So this here is the spark gap that I first displayed in the last video. It's just a PVC pipe section with two bolts screwed into either side, and I have my circuit connected here just with these little circular hole connectors to either bolt inside here. So one end connects to the end of the capacitor bank, and the other end goes to the transformer. And then in the front here of the bolts are just these little spheres that you can kind of screw in and screw out to adjust the gap size. So this design is convenient in that it's very easy to adjust your size. You don't need to worry about getting anything perfectly parallel with anything else, or you don't need to worry about managing the sizes between multiple gaps, because there's just one gap, and the surfaces which are facing each other are spherical, so you don't need to worry about perfectly aligning anything to get optimum performance. The other thing is that the surface of these spheres are curved, and they don't contain sharp points on the ends, which are subject to leaking charge when you're trying to build potential across these two pieces. So it does have some pros. Some cons that I noticed are, one, since we only have one discharge surface, which is utilized for every single discharge, the corrosion that builds up on the surface builds up pretty quick. So these require much more maintenance when you're using them, because not like the gaps I was using before, where it's like this design, you get breaks all along the length. Here in this design, you get breaks in basically one location every time, and that wears it wears these parts a lot more quickly than it does with these types of designs, where you get sort of evenly distributed breaking all down the length of the metallic piece. Another thing that I've noticed is that if you try to push this gap too hard, or if you put too much potential across it, first of all, you'll get a characteristic change in the arc, which you see. So when you get good disruptive discharging, the arc will appear as a white color, and you get a good sort of popping sound. However, if you keep pushing the potential up higher and higher, eventually what you'll notice is the sound goes from a nice crisp sort of popping sound to a sort of steady discharge sound, where it sounds sort of like gas maybe escaping at high velocity from some contained space. And you see the color change from white to purple. And if you see that change, and if you hear that change, what you'll notice is that basically all your output disappears. You're no longer getting your disruptive discharge, but the arc that's playing in between these two spheres persists. So it's not like it's discharging and then breaking and then charging up again and discharging, but you just sort of get a persistent arc that plays between these, which is not what you want for this capacitive discharge circuit. So I'm gonna show you this right now. I can probably do it with the lights on, but first we'll just look at a decent sized gap. So right about there, it's a pretty good size spark gap. It'll give us strong enough current injections. So yeah, I'm gonna turn it on, and we'll look at the sound when we first start to hear it break, and the color of the arc, and then I'm gonna turn up the potential, and we should see that it'll switch all of a sudden to that white color and the good popping sound to a sort of purple color and more of a streaming type of sound. So let's see if we can see that now. I'm gonna go on this side. Okay, got power. Now I'll do it on this side. All right, I'm gonna turn it up. Okay, so that was a pretty good demonstration there. We saw that at first we were getting some pretty good sounding breaking. We were getting that white color, and then as I kept pushing it, we lost our breaking sound, and it turned to a more of a purplish hue. So we can sort of see what that's doing in the circuit here. I have my little handy dandy ground oscilloscope here. I'm just going to use a similar measurement technique that I've used before, where I set the trigger mode to single on the oscilloscope. I'm just going to kind of hold this lead here next to the circuit, and I'm going to get a little snapshot of what's going on. So I have to kind of put the phone down when I take these measurements. So let me just take a measurement real quick. Let me just clear that one. Okay, so that was our measurement. So what we see here is we're getting pretty good looking breaks actually. So we see the energy is charging up the capacitor in this section, and here is our break, and here's another break. So basically we can recognize we're sending in 60 hertz frequency high voltage input to this resonant circuit, and the capacitors are being charged in reverse polarities for each half cycle. So we see here on this half wave for the input voltage, we got two disruptive discharges. Here we get 1, 2, 1, 4. So it's not occurring consistently where we get X amount of discharges per half wave, but we can see that we are definitely getting pretty clean looking discharges where we just get a discharge and then it'll die out slowly until we get our next discharge, and then it dies out slowly. Let me try to just get one more picture of that so you can see it a little better. Okay. There we go. So there's just another example. It does seem like it favors one half wave over the other. We are definitely getting more disruptions or breaks during this part of the wave cycle for the input voltage. Now what I'm going to do is I'm going to turn up the input voltage quite a bit to where we get that streaming sound. We no longer get the white discharge, but we get the purplish streaming. And we're going to see what effect that has on what's going on inside the resonant circuit. So let me just take that measurement. All right, here we go. So this is what it looks like now. We can see we've lost our distinctive discharges. We don't have any significant amplitudes except for this one here. And it just looks like a more sort of chaotic mess. And this is exactly what's going on in the circuit when we see that we lose all of our potential on the output of the terminals. So this is something that basically rendered this type of spark gap unusable for these experiments. If you want to keep the voltage low, that's fine and well, but I'm trying to get, you know, some good effects on these output terminals, so it wasn't really working for me. We need something that's going to be able to quench that spark each time it breaks so that capacitors can be allowed to charge up again and then discharge disruptively once again. So now we're going to swap out this spark gap for the other one, and we'll see the performance difference between the two. Okay, so now I have swapped out the capacitor for this one. It's another multi-gap design, similar to the last one, except it actually has more copper pipe sections than before. So the last one I had 3 copper pipes, making for 2 air gaps. Now I have 5 copper pipes, which makes 4 different air gaps. And I'll just turn it on real quick just so we can sort of see what this looks like. I guess off the bat, some pros and cons of this design. Unlike the other one, we do have to take some time and kind of carefully align this thing to try to get these pipes as parallel as possible. It is adjustable, so by twisting the spark gaps, you can decrease or increase the size of the gap between them. That's why they're all mounted with only 1 bolt, so they can pivot around the bolt. It's adjustable. It does take some time. And if you do it, you know, if something is off, you'll decrease your performance, but it's pretty easy to see if it's misaligned. And you'll see if it's aligned well, we'll get braking occurring all down the length of this. But if it's misaligned, where if one side is, you know, closer than the other, you'll just see that all your braking occurs on one side. So it is pretty easy to see, you know, if you're about right on or not. Let's just turn it on real quick. Okay. So we saw that we were getting pretty good braking going across all the lengths of the copper pipes. So that's looking pretty good. Some immediate things that I noticed with this one is, whereas before with the other gap, we had it where if you push the voltage too high, you would not be able to actually quench the gap. This type of design does not seem to have that problem. You can pretty much keep pushing it, and this will keep disruptively discharging, and you'll maintain your output on the outputs of the transformer, regardless of how much you push the input, or at least within the bounds of what I can do here with my little setup. So we never actually get that characteristic change where it goes from white to purple, and we get that sound where it goes from sort of a popping sound to a continuous gaseous stream kind of sound. We can push this one just about as far as we can here. So I'll just kind of show you here. I'm turning it up. Starts to break. And I can just I'm gonna keep turning it up, and we'll see it keeps breaking, right? definitely much more preferable to what we had before. So I maintained really strong output potentials during that entire run from no voltage to high voltage and back down. I never lost potential on my terminal due to the spark gap not quenching itself. So now we'll go ahead and just do the same oscilloscope snapshots as before. So I'll take a low voltage input one here. Looks like I gotta shut it off. One thing you'll notice when you work with high voltage, high electrostatic intensity stuff, especially stuff with this disruptive discharging of capacitors, is electronics do not like it. So this thing, as soon as you turn this on, it just starts to kind of spaz out. All right, I'm just going to take a snapshot. That's why it's on the floor and not directly next to it. Probably doesn't make a bit of difference, but anyway. Couldn't even get anything with that one. I gotta power it down again. I have to switch the trigger mode to single before I turn on the resonant circuit, or else it just freezes. But now we should be able to get it to work. Gonna restart it one more time. I'm gonna move the probe a little further away. All right, well, it seems like maybe the strength of the dielectric field surrounding the spark gap is just a little bit too much for the oscilloscope. Because honestly, it freezes as soon as I turn this thing on. So anyway, you'll just have to trust me when I say that if we were to analyze what the waveforms looked like in this thing, we would see that as we kept turning up the input voltage, we would continue to see good disruptive discharge behavior, where we get the distinct spikes appearing on each half wave of the voltage input cycle. It would never go to that incoherent, messy, low amplitude sort of noise that we were seeing before, because of the maintenance of the gap where it was not quenching itself. But because this quenches itself very nicely, we maintain good disruptive behavior across our full voltage input range. So that's about it, I guess, for this video. That's kind of what I wanted to show. Got some other stuff coming down the pike here, but I'm trying not to keep these things too long, so I'll just probably cut it off right there for now. But yeah, definitely this design seems to be much more suitable for these types of experiments because of that quenching factor that you get. The other design really is not very usable. It pretty much restricted, what you can do with the bench setup here. So I would definitely recommend this type of design.